My name is Dave Minturn. I'm a principal engineer. I'm actually in the non-volatile memory solutions group. So, and using the Intel 800 series for the NVMe over fabrics. So the agenda, like I said, Fred and I are going to sort of split this agenda. I'll do the first couple sections, more on the NVMe over fabrics introduction and deployment models and how it layers over the top of Ethernet, the various transports and such. And then Fred will take it and describe how specifically how the 800 series is used and how it maps into this architecture, and then some performance and deployment considerations. Okay, so what is NVMe over fabrics? It's been pretty advertised over the last maybe 3 or 4 years, but basically we started out with NVMe being a interface to an SSD that's attached to a PCIe bus. That's how NVMe started its life. I want to say maybe 8 years ago. And the reason we did that was we really needed an efficient model that would scale up to the performance of the non-volatile memory technologies and also the buses. So there's some basic premise behind NVMe itself. It's essentially a high performance multi-queue interface. And I wanted to sort of stress the multi-queue part because that's how we, how it sort of maps into some of the technologies that are available on the Ethernet transports. So what became apparent is, once we had the NVMe defined for PCIe, we had sort of a mismatch with our network protocols. Everything that was block oriented was SCSI protocols, and they were causing inefficiencies, when running across SCSI protocols and then hitting NVMe drives in the back. So we said, okay, we have to fix this by adding, essentially enabling NVMe model, an architecture model over a range of data center fabrics. So what we started with first was RDMA was sort of a natural thing to start with because it was high performance and had multi-queue interface. So one of the first things we did is we defined the NVMe RDMA transport, and the way we defined it was such that it was RDMA provider type agnostic. That's something the SCSI folks didn't do, mainly because of the timing and such. So basically, the RDMA transport maps to multiple types of RDMA, including InfiniBand, and then as it maps onto Ethernet, it maps onto the RoCE and the iWarp provider types. Sort of in parallel, the fiber channel industry picked up on sort of the benefits of the NVMe over fabrics and the fact that their fiber channel arrays were having NVMe SSDs in them. So they defined it in the T11 group for a definition of NVMe over fabrics for fiber channel. The most recent addition is NVMe TCP. And really, what we saw was, folks that wanted to deploy NVMe over fabrics, wanted to use, some of their existing data center network ecosystem, and TCP was the sort of the universal transport in those environments. And so what we did is we wanted to enable that as an option for NVMe over fabrics. And essentially, with all these transports, and there's quite a bit of data and testing out in the public, but it's really, significantly improved, the SSDs, but then also it is the most efficient block storage protocol. It's significantly more performant than, the predecessors, the SCSI predecessors. Okay, and this is sort of a high level of the deployment models that you're seeing. One of the things that you see with the evolution of the NVMe SSDs is the capacity is growing, quite a bit. You're starting to see, SSDs with capacities, in the 16, 32 terabyte, and they've folks deploying solutions with direct attached SSDs are running into some issues with the shareability, sort of like actually they term it sort of stranded capacity. And so what's happened is a model of being able to disaggregate that storage, essentially share it, put it out on the network, a pool of it, and to be able to share it efficiently, amongst the compute. That's, one of the primary usage models that you'll see for the NVMe fabrics is to do that type of a sharing model and do it efficiently, trying to retain the same efficiency as the local attached storage, but, having a pool of it. Another model that you'll see is what they call hyperconverged, and here what you would see is it has the local attached SSDs, but then it also has an efficient way to be able to go to another compute node's local attach and get at it remotely. So, it's sort of a hybrid between, the direct attached and the disaggregated. And the last one is really, sort of a migration. What you see is in storage systems, that have typically used SAS, for instance, serial attached SCSI, as their back-end fabric. As they've transitioned to NVMe SSDs, they needed a back-end fabric that would scale out, and have the same efficiency. And what you see in these type of environments are, for instance, what they call EBOFs, that will attach, to the NVMe fabrics and provide, sort of a basic pooling service. And then those are attached to, multiples of these storage controller front ends. And you're seeing systems come out with that type of an architecture. One of the things too, on the right side, some high points here is, different types of usage model, ephemeral, where they just want to have fast, temporary storage, not have it directly attached. That's one of the usage models for having it disaggregated. And then tiering, being able to dynamically compose the compute resources and the storage resources independently, without losing efficiency. And then as this NVMe Fabrics has been scaling, as we start to see a large number of endpoints, essentially, there's been work in the management area, specifically around the redfish swordfish, and actually was announced last week that the swordfish came out with the NVMe Fabric support. And what this allows is sort of management of large deployments of NVMe Fabric endpoints. Okay, if you look at a sort of pictorial view of the model of deploying NVMe fabrics on Ethernet, and then there's some sort of common models here, depending on what the storage requirement is within the data center. And so what you see is in certain cases you'll see storage being disaggregated at the rack level, where they're wanting to within a rack provide a pool of storage at a high performance, either as ephemeral or JBOFs or possibly even for some durable. And then also as I described before, sort of this back end storage node, where you see some of the compute being the front end storage processing, and then the back end being attached in the same rack with with NVMe fabrics that way. The other model is, is across racks, where you're creating a pool. This is typically, durable storage, as opposed to ephemeral. So you'll see sort of a scale out cluster of NVMe Fabric durable storage service that's being provided to compute resources that are, somewhere else in the data center, not on the same rack with the storage. And so what you see is sort of a range of deployments, that depending on, that map differently to, the data center Ethernet topologies. Okay, so the Ethernet transports that are defined, within NVMe Fabric, there are really two, that are primary map to Ethernet, and one being, the RDMA transport. And as I mentioned before, the definition of that transport is agnostic to the type of RDMA it is. In the case of Ethernet, the two predominant ones are the Rocky V2, which is a UDP-based sort of InfiniBand over UDP, more or less, and then iWarp, which is based on a TCP transport, with a layer of RDMA logic over the top of it. It's And then NVMe over TCP is the one, like I said, the most recent one that was added to, to be able to be used on any type of network, essentially. Okay, so the layering, this is sort of a pictorial view of what the NVMe layering is, and the top blue one is common to all NVMe, whether it's any transport, whether it's PCI or fabrics, so what you have is a host side and a target side or a subsystem side, where the subsystem side is providing the NVM. As it goes down, into the Ethernet transports, what you see here is there's something we call capsules, which is essentially a capsulation of the NVMe commands and completions, and how those are mapped onto multiple queues. In the case of RDMA uses something I call queue pair, which is basically a bidirectional queue that's established between the two endpoints. We map NVMe queues directly onto that. For TCP, we use a TCP connection, which is a bidirectional, and then we map the NVMe queues, it's one-to-one onto those connections. So we basically retain the NVMe multi-queue model, and we're mapping it onto the various queues and end-to-end connection models that both RDMA and TCP provide. If you drop down below into the network layer, this is where it becomes less storage and more networking at this point. You see Rocky being UDP, and because it was sort of built over, the InfiniBand model, it's somewhat sensitive to packet loss. Its recovery methodology is really gets challenged when you start to get heavy packet loss. So it's primarily looked at as being put over a lossless Ethernet type of a deployment, with the data center bridging. If you look at iWarp and actually the NVMe TCP, they're both over TCP. So in that case, it doesn't have that same requirement. It uses the TCP congestion algorithms and retransmit algorithms, and such. Okay, so this is sort of a rough comparison of, what transport would I use when, essentially? And what you have is the two RDMA transports. And, the one thing to call out on the top, network infrastructure is, they require RDMA NICs on both sides and of the same type of RDMA provider. And the Rocky one, as I mentioned before, lossless Ethernet switches in there, the iWarp, standard. As you go over to the TCP, here's where you can use a standard NIC because it is using a software-based TCP typically, the stack, and then standard Ethernet switches in there. ADQ just basically provides optimizations over the top of the TCP. So I mentioned multi-queue, and you'll notice in the description of ADQ, it's all about getting the packets into different queues and combining transmit and receive queues and such. That's exactly aligned with what we do with NVMe. So being able to scale queues onto CPU cores on the host side efficiently, that's where ADQ really helps out with the NVMe TCP mapping. And then looking down at ease of use, what you see is the iWarp sort of standard configuration. As you get into large scale Rocky networks, you'll see lots of papers and such where additional network configuration is required, to sort of deal with congestion and packet loss. And then the other two, the TCP and ADQ, same thing as using the TCP model. It's what you'd see for the RDMA is typically rack level, and then also data center wide with the iWarp, because of the TCP characteristics. With the Rocky, I think it's predominantly rack level within the lossless Ethernet domain. If your domain can span multiple racks, then you see those type of deployments as well. And then the last one is the TCP being data center wide.
Thank you, Dave. I'll talk over Frank here. This is Fred Zhang. I'm the product marketing manager at Intel. I work in Ethernet product group. So, like Dave mentioned, we have a lot of different Ethernet transport protocol to support NVMe over Fabric solution. For Intel Ethernet 800 series product, we actually can support all those Ethernet-based transport. We can support RoCE v2 and iWarp, but we actually can support them concurrently on a single net. And with RDMA, we can deliver very low CPU utilization in low latency and low latency jitter as well. NVMe over TCP with ADQ enhancement, you can get those kind of improved throughput, reduce the latency, and more importantly, reduce the latency jitter. And for the stateless offload engine on our controller, you will also get the benefit of those improved efficiencies through those use of multiple generation kind of improve the TCP stateless offload engine. The last thing I also want to highlight here is the capability to deal with the congestion. This is very important for the deployment in a scaled network, in a large network deployment in data center. And you can look at the table on the right side. For different Ethernet-based transport, we actually have multiple congestion control technology that can help the transport to deliver the performance in a congested environment. There are mainly two major congestion control mechanisms in the large network data center. One is the ECN-based, explicit control notification-based, which means a switch actually will flip the ECN bit and tell the endpoint that congestion is going to happen. And the other one is the round trip time based, and that's timely, that can measure the packet round trip time and decide whether there's a delayed round trip time and I need to control the packet pacing. So you can see for iWarp, we support the default TCP, congestion control mechanism. We also support the baseline ECN, and then we support DC TCP and timely. For RoCE, we support baseline ECN, we support DC QCN, DC TCP, and timely. And TCP will just map whatever iWarp can support and can provide all those kind of capability. So with all those congestion control mechanism, Intel Ethernet 800 series product actually can support NVMe over Fabric solution in a large network deployment and deliver the performance when congestion is happening. I want to switch the gear to talk about some performance data that we measured. But before we get into the actual data, I want to show the diagram of the test environment. So in this data set, we want to show the ultimate performance without considering other bottleneck. You can see this is a back-to-back configuration without a switch sitting in the middle. On the target side, actually, we are putting a very powerful Xeon Platinum, Intel Xeon platform that can provide a very powerful CPU processing capability. And on the storage on the target side, we put 6 Intel Optane SSD DC 4800 drive, which are very powerful with high IOPS, so that we don't get into the drive bottleneck. And we use two 2 by 100 gig Intel Ethernet adapters on each side, so that we can measure the performance of this end-to-end configuration. The purpose is to measure the performance of a true 100 gig connection running NVMe over Fabric with different Ethernet transport. So here's the performance data. So we're showing two sets of data. On the left side, this is a 4K random read workload running on both sides with different kind of Ethernet transport. We're using QDEP 16, and we only measure the 4K I/O size. We have RDMA iWarp, we have RDMA RoCE, we have NVMe over TCP, and also ADQ enhanced NVMe over TCP. You can see the IOPS data on the left side. All of those Ethernet-based transport can deliver fairly good performance. Averagely, they can deliver above actually 2 million IOPS for the 4K random read, which is a very high IOPS for a single physical host. Specifically for iWarp, both IWAP and Rocky V2 can deliver fairly similar performance. We are getting over to 2.7 million IOPS per second. NVMe with TCP is a little bit behind, but it's still above 2 million IOPS. And with ADQ enhanced NVMe over TCP, you can see the NVMe over Fabric solution can get to almost the same as NVMe over RDMA solution. On the right side, we're looking at the latency. And in the latency measurement, actually, we are doing things in a little bit different way because we just want to measure the latency on the wire instead of, including the latency of the data accessing on the drive. So we create a new block devices on the target side, and we just measure the round trip time on the wire. You can see the comparison among all those Ethernet-based transport. IWAP RDMA or Rocky RDMA deliver the lowest latency. We can get to around 25 microseconds. That's a round trip on the wire with a 4K random read I/O request. For NVMe over TCP, we are seeing a little bit higher round trip time on the wire. And with ADQ enhancement for the NVMe over TCP, you can see the latency was improved significantly. And you can see the latency is almost, the same as NVMe over RDMA. It's pretty close. And this data actually was measured on a slightly older Linux kernel. That's a Linux kernel 5.2. And with latest Linux kernel, you probably will be able to see much more improved performance for NVMe over Fabric using Ethernet transport, especially the latest in Linux kernel 5.8. Detailed configuration can be found in the backup slide, 50 to 55. You will see all those kind of detailed configuration. Then I want to show a little bit more performance data based on the latest measurement. You probably have seen the news announcement from Intel that Intel and the Lightbits are getting into a strategic collaboration. And this collaboration will cover not only technical, but also sales, marketing, and ecosystem enablement. With all those kind of effort, joint effort between Intel and the Lightbits, will push the boundary of storage, NVMe over Fabric storage solution in performance, flexibility, and also the total cost of ownership. This optimized storage solution will include Lightbits, LightOS, will include Intel processor, Intel Ethernet product, Intel 3D NAND SSD, and the Optane memory, and also our leadership FPGA products. On the right side, you can see some of the data published on the white paper, and you can find the complete report of the performance in the link on the bottom for more data. But on the right side, we're only showing the single thread performance data with different QDAPs. You can see the comparison between the throughput performance on the top between the ADQ and non-ADQ. The significant, throughput, improvement with ADQ enabled. On the bottom chart, we're showing the latency data. We're showing two latency. One is the average latency with ADQ and without ADQ, and we're also showing a 99.99 percentile latency, ADQ versus non-ADQ. You can see those significant differences between ADQ and non-ADQ workload. So overall, we are seeing over 30% predictability improvement. We're seeing 50% improvement of the latency, and we're seeing 70% improvement of the total throughput. So more data, you can refer to the white paper on the link on this slide. So to add the performance attribute to what they've talked about regarding the network infrastructure, OS, stack, EDF views, and also user model of different Ethernet transport, you can see NVMe over TCP actually provides a baseline IOPS and the CPU efficiency. It has a little bit higher tail latency, but it can work across data center. On top of NVMe over TCP, you can get additional enhancements with ADQ. You get improved efficiency and also a lower tail latency. And with RDMA iWarp, or RDMA Rocky V2, you get highest IOPS, you get lowest CPU utilization, and also lowest tail latency. To conclude what we talked about, Intel Ethernet actually can support all those Ethernet-based transport for ME over Fabric solutions. We offer multiple adapters in different port configuration and different form factors. On the right side, we're showing 2x100 gig PCIe form factor. We have 4x25 gig, 100 gig throughput adapter. We have 2x25 gig adapter. We have adapters in standard PCIe form factor, and we have adapters in OCP 2.0 or OCP 3.0 form factor for those high density storage solution designs. We also provide different, congestion control technologies, and those congestion control technology can provide a performance in a large scale network in a congested, network traffic. And all those kind of Ethernet-based transport provide the flexibility to our customer, and the customer can choose whichever that can suit their use cases based on their workload, their I/O patterns, and also their network topologies. ADQ actually can further improve or enhance the performance on top of standard NVMe over TCP deployment that can provide a higher throughput, lower and more deterministic latency. We have already launched Intel Ethernet 800 series controllers. You can find the detailed product information on this link. We have also launched the leading adapters, including 2x100 gig and 4x25 gig adapters, and 2x25 gig adapters as well. You can find more detailed information on this, link on the bottom as well.